There are many gurus also in that respect, gurus in their own field of operation. So welcome to you all. Coming to SGAT, the Society of Geoscientists and Allied Technologists, came into being in 1981, and ever after that, this is actually trying to be a fraternity of true professionals in which geologists, geophysicists, and also allied technologists are present here. And last evening, we had a dry run with Professor Bibhuti Mohanty, and he was talking about the largeness of the University of Toronto, with close to 100,000, 1 lakh, as you say in India, number of students, undergraduate students, postgraduate students, faculty members, so very large. And so therefore, the subject of geology or geophysics or mining or even civil engineering, they are all integrated together. There is no system today, not even history or archaeology, which can operate in silos, and they are all integrated systems, multidisciplinary. And these multidisciplinary approaches, I'm not surprised when he talked about it, that they don't work in isolated silos. And that's why he is in the Department of Mining and Civil Engineering. As far as India goes, we still have some kind of silos in many of our colleges, in IITs, in some centers have improved. And most important thing is the learning from various disciplines. And that's where actually the disciplines are, each individual discipline is widened. One other thing which I remember also today being a Guru Purnima day, that whenever in the earlier times, 50 years back, when the disciplines of engineering started in India, we were talking of civil engineering, mechanical engineering, metallurgy, or mining in various silos. And today, the engineering per se, engineering discipline, we talk of science-based engineering. And the science-based engineering, by the very definition, also brings together a number of disciplines. And one other connotation is there of the science-based engineering, and that happens to be quantification of the engineering sciences. Gone are the days when we would talk of the empirical sciences only. Empiricism still operates, and still operates quite widely and also deeply. But today we are talking of the quantitative approaches to every engineering approach. And no quantitative approach would be important or accurate unless multidisciplinary approaches as possible. So that's why we feel very proud and privileged that we have a speaker who belongs to a multidisciplinary department, and he has given us a topic, the mining technology, safety, and economics, which are also multidisciplinary approach. I would also recall on this occasion that India is aspiring to go big on the mining sector and the metallurgical sector. And when we talk of the Indian steel technology, for example, I talk steel because I feel slightly closer to steel, having spent some years with the steel technology after my IIT Kharagpur teachership for 20 years. So in Tata Steel and the other steel plants that I have seen, if India is today operating at about 116 million tons or 119 million tons, at that we are number 2, but China is above 900 million tons out of the 1900 million tons in the world, and India is aspiring to go to 300 million tons in the year 2030. But to go to 2030 to 300 million tons, we would require close to 490, let's say 500 million tons. So thumb rule would be 500 million tons of the iron ore we would require. And not just that, all of us, or all those who would know about the steel making, iron making, we know very well that in the blast furnaces, at least up to about 6 years back, we were only talking of a 2-component burden system where the sized ore and the sinters were there. Today, most of the steel plants work their name in the world, and in India, although we are newcomers, but most of the steel plants, including Tata Steel, we are all for 3-component systems, in which we talk of the sized ore, we talk of the sinters, and we talk of pellets. That means the use of fines. So today, we have actually a number of steel plants who operate on fines. Through the slurry transportation, they collect the fines and they make pellets. And the blast furnaces have learned how to operate the 3-component systems. When you talk of the aluminum sector, India is around 3.7, 3.8 million tons. Let's say roughly 4 million tons. And if the world is talking of 63, 64 million tons, and China is more than half of that, So India, if it has to talk of 10 million tons, multiply by 6, so that many million tons of bauxite ore should be necessary. I only talked of these two, but the other day, whole of India, we are talking of the rare earths. So the rare earths and their ores, they are so important. But India talked of, the world talked of actually the breakthrough technologies in which the new technologies are coming up, in which digesting, let's say, the telephones, the microphones, the micro sector, that means the cell phones, and then collecting rare earths from that. Why rare earth has become so important? Because the Chinese have otherwise monopolized more than 90% of the rare earths of the world. So therefore, these are all extremely important things, but mines are very important. And for the mines to be important, geology and geophysics should be important. And the safety of mines should be important. And the economics, of course, is most important. But above all is and sustainability. So I think all I'm trying to say is SGAT over the past over 40 years, it has actually started interacting with the government sector, private sector, and so on. And after 1995, when we published our first book on the geology and mining or mineral resources of Orissa, and this year or 2020 December, we actually come out, 2021 January to be more precise, we come out with the 4th edition of our book called the Geology and Mineral Resources of Orissa. But the geology and mineral resources of India would be extremely important. And for that, all the 3 areas, sub-areas, which Professor Bibhuti Bhushan Mohanty is going to talk about, will be extremely important. So with that, I welcome Professor Bibhuti Bhushan Mohanty, eminent scholar in his own area. And it is not only the 3 top companies of the world in the US, where all the top, not just the CEOs of that company, but they are of the group heads. I'm not just talking of Satya Nadella of Microsoft, where he has become the group head. And it's just him. We are talking of also the IBM head. We are also talking of the Google head. And incidentally, Google head happens to be from IIT Kharagpur Metallurgy department. But apart from these 3, there are many important professors like what we see from North America. They have, fortunately, some of them are with us. They are also very important. So we welcome you all. I have great pleasure in welcoming you all once again. And over to you, back to you, Mr. Sujit Mohanty, our anchor. With that, I wish you a great time in today's seminar. And this seminar happens to be, as Sujit Babu said, we have started what is called the Distinguished Lecture Series by SGAT. And this is the 3rd lecture. And in the 3rd lecture, we have Professor Bibhuti Mohanty. Over to you, Sujit Babu.
Thank you so much, sir. Now I request Girija Prasad Mahapatra, former Additional Director General, Geological Survey of India and Vice President SGAT, to introduce our esteemed speaker, Professor Bibhuti Bhushan Mohanty. Sri Mahapatra, please.
Thank you. Thank you, Sujit. And good evening to all my colleagues and friends. And good morning to Professor Bibhuti Bhushan Mohanty and Bibhuti Bhushan Mohanty also. So it is my privilege to introduce our honorable speaker for this evening. Professor Bibhuti Bhushan Mohanty is a graduate of IIT Kharagpur. Although I think his native place is Puri, and his schooling and college education in the preliminary stages, it was both at Puri as well as Bhubaneswar. But he graduated from IIT Kharagpur, BSc and MTech in Exploration Geophysics, and he obtained his PhD in physics at the University of Toronto. Following that postdoctoral work at the Texas A&M University, he joined the Explosive Research Laboratory of Imperial Chemical Industries Explosives, now Orica, which is an Australian company, I believe, which was the world's largest manufacturer of commercial explosive and accessories in the Montreal, Canada. Dr. Bibhuti Mohanty is a professor emeritus in the Department of Civil and Mineral Engineering, University of Toronto. Presently, he is also a distinguished visiting professor at IIT Kharagpur and a visiting professor at the China University of Mining and Technology, Beijing. He has also taught at McGill University, Montreal, Canada. Dr. Bibhuti Mohanty prior to his assessment as a whole, the portfolio of as the chair of the Industrial Research of Natural Science and Engineering Research Council of Canada, that is NCERC, at the University of Toronto. Prior to this assignment, he had the chair also the same thing. As a senior science and technology associate, he headed a team working on the commercial explosives and its application over nearly 25 years. His interests are in the field of explosives, rock blasting, dynamic fracture of materials, comminution, explosion hazards, and blast resistant structures. It involves investigation of
Why you have to unmute? It's why mute agent.
Once again, it has become muted. Girijababu, you are once again muted inadvertently.
muted me.
Yes, now it's okay.
Okay, sir. Anyway, sir, his research interests are in the field of explosive rock blasting, dynamic fracture of material, comminution, explosion hazards, and blast resistant structures. It involves investigation of fully instrumented and controlled laboratory scale tests to full scale open pit and underground blast for development of predictive numerical tools in the blasting and fragmentation. Understanding dynamic fracture behavior of rock is a key step in quantifying response of rock mass to high energy transient loads such as in drilling and crushing of a rock and fragmentation due to explosive action. This is integral to all civil and mining excavation activities and determines the safety, economic aspect, and viability of operation. He is a widely published author in all these areas. He is also founding member of FIOC, that is the Frag Blast International Organizing Committee, the body responsible for organizing periodic symposia of rock fragmentation blasting, and a member emeritus of the International Society of Explosives Engineers. His research at University of Toronto has been supported by grants from Natural Science and Engineering Research Council of Canada, Ontario Research Foundation, Center for Excellence in Mining Innovation, and leading mining groups such as Valley Canada, Barrick Resources, Newmont, and Sandvik Canada. We will be honored to have his presentation from Professor Bibhuti Mohanty on such a dynamic studies. Thank you, sir. I think we will be listening to you. Handed over to Sujit. Sujit, please.
Many thanks, Mr. Mahapatra. Now it's a proud privilege on my part to request Professor B.B. Mohanty to make his presentation. Professor Mohanty, please.
Namaskar. Thank you very much. I tried to share the screen and it says it's disabled by the host.
Please retry.
Sujit, can you enable him immediately?
Sir, it is audible. He is audible very much.
No, not audibility.
Yeah,
He's
no.
talking of sharing.
Says you have to do it.
Sir, it is done, sir. Please
It is done.
retry, sir.
So, Professor Bibhuti Babu, why don't you try if you wanted to share your screen?
Sir, you try once again.
When I try to share a screen, it says disabled.
Even now it
Okay.
says disabled.
I think now it's coming in right now.
Yeah.
It is done, sir. It is done from my end. Sir, could you please retry, sir? Sir, could you please retry? Now?
Okay, let me try again.
Correct, sir. Yes.
Yeah, now it's okay.
Okay.
Your screen is at least you are viewing it. It
My
says
screen is working. Yes. I'm trying to get my PowerPoint.
yes.
No problem yesterday. What happened here today?
Sir, you have to go to your file position and then share it.
Yeah, you bring your file onto the main screen first.
Yes, I'm trying to.
No, explode the PC, sir. Better to explode the PC and then the file wherever it is there. You have to. Right, explode it, sir. Right, explode.
Yes.
No, not
Just a
explode.
second, please. Just a second.
Yes. That's the one. No. Correct.
I think your file is now visible.
Yes.
These are all the files, yes. Take your time. Take your time.
Yes. I'm sorry for this, but
No. Take your time. Don't worry. I think it can happen.
And make a search there, sir.
Whatever is your file name, if you remember that. So what happens is usually this, the file is there, but the file name,
yes.
it has to be a PowerPoint. So the PowerPoint is down below. I think we saw a number of PowerPoints.
Yes. That is why I don't see this particular one.
I believe since you had displayed yesterday, it will be in the recent files also.
Recent file देखिए पाई परिवे. Because you had shown, did you open that file yesterday? Same file?
Yes.
Yes.
So अपना
as per date भी मिल जाएगा.
Date रे अपना पाई परिवे. Because these are all old. 14, 15.
Yes.
Neguda nuhe.
2021.
You are searching in the documents.
Yeah, documents, that's right. Eguda nuhe. Best होचे date को चल जिबारा. Excel
Acha.
PowerPoint को चल जाए तो PowerPoint, just open your PowerPoint and then you'll get it. ସେଥିରେ date ଦେଇ ଦିଅନ୍ତୁ.
ସାର୍ଚ କରିଦିଅନ୍ତୁ ସାର୍, ସାର୍ଚ କରିଦିଅନ୍ତୁ.
ସେ ଫାଇଲଟା ଆପଣ ମାନ ଆମ ପାଖରେ ଅଛି କି ସୁଜିତ ବାବୁ?
नहीं ଆମ ପାଖରେ ନାହିଁ sir.
ସେଟା ଭୁଲ ହେଲା. ହଁ ଏଇଟା ଦେଖିଆ, ଏଇଟା this is the one.
SGAT. Yes.
So your tension has ended.
Yes, hopefully, hopefully.
Yes. Whenever the Zoom thing starts, we all go through that whenever there's a big thing. Okay. Again.
Okay, hope everybody sees this. Again,
Yes,
my
we all-
apologies for this delay. So as we discussed yesterday, I'll be talking on mining technology, safety, and economics, a systems approach.
Excuse me, our video is stopped and microphone. It's okay.
No. Everything is working.
Already, everything is working.
At your end, there is a problem.
No, we are able to hear and see everything very clearly.
Yes,
Please
we're
continue.
all able to see. Please continue, Professor Bibhuti Bhushan.
Okay. So actually, excavation and mining involves rock fracture and fragmentation. Also involves explosives, initiators, safety, economics, and the associated issues. Rock excavation and fragmentation essentially is a comminution process, which means you reduce from a large size to a small size. That gives you a sort of background, and when I say comminution, a size reduction process. Okay, this is your in situ. Either rock exists, and you can see the scale here. It's from meters to tens of meters. Okay, then we have the draw point where the rock is deposited or the fragments are deposited after the blast. The subsequent operation is crushing, and then next is rod mill, SAG mill, and ball mill. So all these are essential processes before you can extract the element you want. So essentially, all these are size reduction processes. It can be done by impact or through explosives. So scale of a blasting operation, for example, I'm confining myself to the blasting topic at the moment. The borehole diameter can be anywhere from 25 millimeter to 380 millimeters. Explosive load per hole could be 1 kg to 1,000 kg per hole. Bench height could be 5 meter, 25 meters. Number of holes could be 10 holes to 500 holes. And of course, you don't set them off at the same time. There are delay between the holes going off, and that could be controlled and programmed from 0 to 250 milliseconds. I'm just going to give you an example of typical excavations scenes you see. This is a road cut, for example, and you can see that the walls are vertical. Actually, you can see the remnant of the holes, the blast holes. See, there's another picture of a typical road cut anywhere in the world. That's the underground operations. So you can see the scale here. Okay? It's very large scale, and you can see from the scale, you can see the workers and the boreholes. This is all around, designated by red flags. And then you have the so-called open pit mines. So you can see you have a whole range of scales we're dealing with. Of course, each requires a different technology. You can this is open pit mine, and typical blast design for large capital projects. So this is a blast design for a large one. I'm not going to go into detail. I'm showing you the whole locations, and of course the numbers are timing. Okay? The point I'm trying to make is that you can't just, with the large scale operations like this, you can't just go around and do it arbitrarily. You have to design in mind. You have to know the response of the rock in question, and each operation is specific to the ultimate objective you have. So kind of coarse fragments or large fragments in coal mining, whereas fine fragments for gold mining, for example. And of course, you want to also excavate only the area you want to work and not damage anything nearby, adjacent rock slopes, etc. So it really involves, as I said before, it's really a system approach. It's a multidisciplinary. It's actually mining must be the most multidisciplinary topic that you deal with. It's material science, detonation physics, thermal chemistry, transportation and materials handling, explosion hazards and protection, of course, and environmental issues, which are much more critical these days, and of course, eventually the economics. You have to make it economic to make it work. So I'm listing a fracture dynamics of in blasting itself. The rock itself is, of course, very important. You have to look at the microstructure of the rock. You're looking at explosion-induced fractures. When you say explosives, of course, you are applying load at a very rapid rate. I'll give you some examples. And the response of materials is not the same as due to static loads. And of course, ultimate goal with the scale of operation that I showed requires that we have a pretty good idea of what results might be. You can't say, oops, I made a mistake, I have 1 million tons of rock broken badly, let me do it again. You can't do it. So you need numerical models, fracture models, and predictions, okay, which is a different topic altogether. Someday maybe we'll discuss it. But you can see it's a very complex topic. You can't just put explosive in a hole and hope that everything works fine. And I haven't come to the economics yet. Okay, I'll give you a time scale here. Fragmentation of rock or materials depends very much on the strain rate. Crushing and grinding, it's a slower process. Your time scale is 100 milliseconds or thereabouts. Drilling and cutting is more like 10 milliseconds, whereas blasting is less than a millisecond. So a whole range of time scale, 2 orders of magnitude or more, and you want to control and predict. And the essential need in all, practically all mining and excavation operations. Careful tailoring of properties of both rock and explosives. As I said before, fragmentation specific to each mining method. Coal mining doesn't require very fine fragments, whereas precious metal mining requires very fine fragments. And you want to, of course, control the blast-induced fractures and limit damage to remaining rock or buildings or personnel. So energy partitioning, explosive, people who are not in the explosive business, it has both shock fractions and the lower or higher time scale of the operation, and it requires information both microstructural properties of rock and the microstructural properties of the rock. So the rock fragmentation system consists of actually 3 components here: explosive initiation system, plasticides, and the most important part, the characteristic of the target rock. Just a brief example of description of explosives. For people who are not in the field, they would think, well, this is just a very simple thing, just light something, initiate something, and it goes bang. It has to have fuel, oxidizer, and a sensitizer. Okay. For example, fertilizers that use commonly are very difficult to initiate. So they need a sensitizer to cause detonation. So this is an example. Components of explosive, we need 3 components. We need fuel, oxidizer, and a sensitizer. Okay. So thermochemistry, as I said before, it's a multidisciplinary topic, and I'll be covering several areas of physics. Okay. So fuel is carbon, hydrogen, metals, aluminum, magnesium in fine powder form. Oxidizer is oxygen, which you get from nitrates, ammonium nitrate, sodium nitrate, etc. Then, since you are looking at a very large range of diameters, you need to make them sensitive to initiation from very small to very large diameters, which means we need a chemical sensitizer, such as I give you PTN, TNT, which you most people know, RDX, most people know, and nitromethane, etc. Okay? And of course, you can use physical sensitizers in terms of fine microbubbles or air bubbles. And I will not go into that technique, science of it. When you compress an air bubble, you increase the temperature inside the air bubble. And that, if it's high enough, it will initiate the explosive itself. So you don't need a chemical sensitizer. In fact, many explosives today in the commercial field use physical sensitizers like glass microballoons. They are micron size and air bubbles. Okay. There are, of course, military explosives and commercial explosives. Military explosives, of course, TNT, RDX, you all hear about it. Terrorists use it all the time. They're self-sensitized. Whereas commercial ones are in the form of slurries or grains or granular material, emulsions. Sensitizers are glass bubbles, air bubbles, and fine aluminum. I can see the cost difference is order of magnitude. Military is 10. So obviously you cannot use military explosives for mining. You need commercial explosives where we can look at $1 a kilo. Just a brief introduction to energy release. So this is a nitroglycerin that breaks down to carbon dioxide, H2O2, and nitrogen. And the heat released is 1620 calories per gram. It's very large. I'll come to it. Now, is that all the energy available to do the work or not? I'll come to that. Okay. So a typical example today in the mining area is ammonium nitrate plus fuel oil, what we call ANFO. And if we react them, we would get 930 calories per gram. It's very large. But just a small change in fuel content can reduce the energy release by a very significant amount. Here you can see if I went from 5.5% fuel oil to 3.4, I reduced the energy release to only 600 calories. Commercial explosives, of course, there are whole lots of them. There are dozens of them from different manufacturers. I'm not going through them. They have different properties of water resistance, fume class, everything else. Okay. So effective energy, the energy that's deposited onto the rock until the venting occurs, the venting of the gases. Okay. And as I said before, commercial explosives are non-ideal, unlike the military explosives. So you can see here. Hello?
No, sir, please continue.
Okay. So I'm looking at reaction rates for 3 explosives here. As a function of diameter, you can see they don't have the same reaction rates. Okay? The most common used explosive is ANFO, and you can see that its reaction rate changes with the diameter. In fact, you need very large diameters for it to become fully reactive. And so when you say explosives, it doesn't mean that you just put some explosive in the hole and it goes off by itself, or you initiate it somehow. So there are, so what we call here is there are non-ideal explosives. This is the energy from the shock energy from the explosive. You can see this normalized, okay, for a particular explosive here. You can see the energy released is a function of the diameter. Same chemical composition, but the energy release is very dependent on how you initiate the explosive. And the initiation techniques are given here. But you can see there's a big difference between this diameter and this diameter. Although chemically the same explosive. And person outside the expertise would not know this. So as I said before, we have two kind of energy coming out of the explosive, or the shock energy and the gas energy. Shock energy, of course, is very rapid in microseconds, whereas explosion energy, gas energy can be in milliseconds. So you have a very significant time factor in this. How the material responds to this depends on the interaction between the rate of loading, which I'll come to a little later. So it's really going to the material science. And the rate of loading changes the property of the material. So strength for a rock, for example, it's not the same under static loading as it would be under dynamic loading, like shock loading. Okay. And energy changes, of course. This for emulsion explosive. Of course, depending on how you initiate the explosive, your energy can change, your shock energy and your gas energy or bubble energy. Okay, and you can see there's big differences between the way you initiate the explosive. So what I'm trying to say is that when you give an explosive and you have some energy number given by the manufacturer, doesn't mean that you will get that energy released in the borehole itself. It depends on the borehole diameter, also how you initiate the explosive. So I will not go into the material science great deal. It's a very important topic in our subject. You can see all these properties are dependent on the rate at which you apply the load. So fracture toughness, fracture velocity, micro hardness, and of course strength. So there are no fixed numbers as we have in static loads that okay, it's a limestone or it's a steel, it has certain strength. That's not true. I'll use some examples. So these are all, they all have to be known beforehand before you design the blast for a particular mine site or particular rock type. Just an example here. You can see that I've shown you two granites here, okay? Sandstone and Laurentian. what I'm trying to determine is the universal strength of these rocks. That's a static strength here. Okay, this is my load rate. So many megapascal per second. As you can see here, strength is not a constant number as you understand normally. Okay, it's only applied for static loads, but for dynamic loading like explosives or impact, the strength is a function of load rate. So actually the material becomes stronger as the application of the explosive or impact becomes faster. So there is no unique number. All these have to be determined before you design a blast. All these have to be determined beforehand to design your blast. But you can, this gives an idea. So it goes from 250 megapascals to 400 megapascals. Same rock, nothing has changed. All have to change is the rate at which I apply the load. Okay. Then you have hazards and safety, of course. Okay. So gas explosions, dust explosions, condensed phase explosions like liquid, slurries, emulsions, ammonium nitrate, avian for etc. And it all depends on what you look at. When you look at hazards, you look at what's your source. Okay, they're all different characteristics. So type of explosion hazards, for example, the flame and radiant heat, the blast wave, teetering and eject of material, ground vibrations, especially for buildings, and of course, high velocity debris and fragments. It can apply to an open pit mine or underground, or for terrorist activities, okay, and cased ammunition. So I'll give an example. I'm giving an old one here. It happened 10 years ago. It's a Cyprus naval base. Early morning, it had a shipload of explosives, and it went off. Luckily, it happened very early in the morning, so only 25 people got killed. And the port was partially destroyed. Electrical supply was down. 30% of the country didn't have any electricity. If that happened little later, say 10 o'clock in the morning, you would have had a lot more casualty and damage. And a good example is what happened to Beirut explosion 2 years ago, where the fertilizer grade ammonium nitrate was stored, has been stored for a couple of years, in a large silo. It caught fire and eventually detonated. And of course, killed quite a few people in Beirut. The whole port was destroyed practically. You can see that you can have all kinds of effects due to the accidental explosions, either deliberate or accidental. So I'll give you an example of the damage you're looking at. This is the actual structure we built. And we put 24 kg of explosives inside. Now I would like to show you what happens. Okay. It's a full-scale model. It's a small one, only 24 kg. Okay. Then you cover that with cement blocks around, like a typical magazine, explosive magazine, and we did initiate it. Okay. Of course, high-speed cameras to see how the fragments behave or velocity they come out. And that's the result of the explosion. That's only 24 kg. As I said before, we have 1000 kg in a blast hole, could have 1000 kg in a blast hole. Okay? So you can see the power of the explosive itself, and was completely destroyed. So it's not the fragments only. We also look at the velocity of the wind following the explosion. And incident pressures are given here from 345 to 13.8 kilopascal. And the dynamic pressure, we will not have occasion to discuss these various terms in this talk. Hopefully someday we'll look at the detonation process itself. But you can see that the pressures are very large, and what for the non-specialist, what would be more important to see the wind velocity. You can see the wind velocity are extreme. Even it's 13.8 kilopascal, which is actually the typical atmospheric pressure. This is overpressure above the atmospheric pressure. The wind velocity is 115 kilometers per hour. And with a slightly higher amount of explosive, you can get to 1000 kilometers per hour. So you can see what damage it might cause, or it would cause to surrounding community or the building. So the hazard is a multifaceted topic. Fragments, damage due to the high velocity winds, and of course, collapse of the structures. So this is giving an example of typical wind velocity. For example, baseball, you get 45 kilometers per second. Tennis ball, 65. Cricket ball, 42. Okay, but if you went back there, you can see the change in the velocities, and you can see what damage it can cause. Okay. Other additional factors are environmental noise, dust, fumes, leaching of chemicals, because you leave the explosion in the borehole for weeks before you initiate them. It takes time to load and other areas of work. So chemicals can leach in the groundwater. And of course, you look at stability of residential structures, and importantly, stability of remaining geological structures, the pit slope stability. The walls I showed you before in the beginning, how flat and vertical they are, undamaged. So all these factors go into your blast design and the blasting operations. Okay. Of course, this is the most important part of the operation. What are the various costs? Suppose you look at all these safety issues, supply issues, initiation, blasting itself. What does it cost? And how do you control it? A mine life depends very strongly on economics. Okay, so I'll give you an example here. Okay, it's a busy slide, but I'll go item by item. So you can see all these functions occur at an operating mine. Okay. So digging costs over 6%, ventilation costs 10%, material handling 17%. It's a typical mine operation. Electrical part, dewatering, crushing, okay, 4%, and grinding, 40%. So in fact, crushing and grinding take up 44% of the cost. Whereas drilling and blasting consumes less than 10%. Unfortunately, in a typical mining operation, even today, these are all viewed as unit operations, like as if they have no interconnection. So the drilling and blasting depends on the drill engineer or blasting engineer, and grinding, etc., depend on the subsequent actions at the mine. But what people don't realize is that a more efficient drilling and blast design can significantly affect the cost of crushing and grinding. Because when you blast a rock mass, you clear fragments. The fragments also have microfractures in them, which helps the grinding efficiency or crushing efficiency. In other words, if I did the blast design correctly here, I could reduce this by, suppose I increase this cost of drilling and blasting by 10%, I can probably reduce the overall cost by 20% here. Unfortunately, most mines, even in North America, do not look at it as a total system approach, but as individual units of cost. Okay? And this is where the challenge lies. We have to economize and increase safety. We have to look at the whole system. And one of the key parameters, of course, is the blast design or the blast engineer. Okay? So economics of energy utilization. So as I said before, drilling and blasting constitute 10% of the less than 10% of the total cost. Crushing and grinding represent 40%, over 40% of the cost. And in a typical mining operation, these two factors are considered independent. Although proper design of a drill and blast operation will result in significant cost saving and thereby extend mine life. Therefore, there is potential for considerable saving of cost in our operation if the two operations were not considered independent of each other, and thereby extend the mine life. I haven't talked at all about geology. Not because they're important, it's very important, but that's a big topic by itself. Okay. So far I've talked about the rock was homogeneous and uniform. Only thing I've changed is the rate of loading and the strength or fracture toughness. Okay? But geology plays as important a role in actual excavation as everything else. So joints, position planes, lithology, inhomogeneity, all these are inherent in a blasting operation or any excavation operation. Okay? As I said, that's a separate topic itself. Someday maybe we'll go into that. But reason I haven't discussed this before, not because I think it's not important, but because it's a very large topic in its own right. Okay? There are not many mines where the rock is perfectly homogeneous and uniform, unless you are blasting granitic blocks. Okay? Of course, we are making progress in the alternate mining technology at the same time. Horizontal raise boring, so large tunnels, hauling truck automation with machine vision. It's already operational in many areas. Automated drilling with GPS, portable solar powered units for remote location. And in fact, you can use the tailing ponds, which are very large in most mines, which are not being used, as a thin film solar panel. So it provides you with electricity you need. Okay. So we really have to look at the whole operation in a holistic manner, so that we make the operation both economically effective and environmentally friendly. The alternate mining technology, as I said, we have unmanned aerial vehicles, referencing back wall stability, joint mapping, measurement blast patterns, stockpile volume, fragment size issues, etc. So we have made a very significant progress in the previous decades to quantify rock fragmentation process in mining. But as I pointed out, only a systems approach involving many disciplines can address the basic issues and yield an optimized solution. I'm always fond of this picture. Some of you may have already seen it. I've been there. It's a temple built in 760 AD out of an outcrop of rock vertically down. So it's not like a typical temple where you carve rocks and assemble them together. This you start from a block of rock and carve it down to the temple. So there are no, and at that time there are no explosives. They're all done by manual labor. And this is the Kailash, famous Kailash temple in Maharashtra. And you can see this is hand carved. This is a scale of this. That's a person there. You can see the scale here. And it's all carved from a block of rock, not joined by cement, or you can see the scale. Incredible. Okay. And finally, excavations, etc., is not only man-made like this one, but also there is a famous crater lake. This is the impact crater. It's perfectly circular, kilometers wide. Okay, this is from an USA crater lake in Oregon, but you can see that so it can be extraterrestrial or man-made. Well, the same physics applies to all this. Okay, I didn't get to discuss the impact crater issues, but you can see the scale here, and then you compare the scale beforehand. Okay, so I thank you very much for your questions. It's a very complex topic. I hope I have given you some glimpse of it. I haven't gone to the details of the physics behind this, but it's a very challenging subject, and we have a lot of areas where you can improve our operations and yet at the same time protect the environment. Thank you again.
Thank you so much, sir, for such brilliant presentation. It now gives me immense pleasure to invite Mr. Sanjay Patnaik to kindly moderate this session. Mr. Patnaik, after completing his mining engineering from Osmania University in the year 1983, joined Tata Steel and served the company and its associate company for long 37 years. He has completed an advanced management program from SGAT and SGAT, France. He was the managing director of Tata Steel Long Products Limited, formerly Tata Sponge Iron Limited, before completing his tenure with Tata Steel with effect from 1st November 2019. He is presently working as Director, Project Affairs and Business Development with SR Minmet Limited, a group company of SR Group, which is putting up to large projects in the state of Odisha. Mr. Patnaik was chairman of CII Odisha State Council during 2016-17, president of FIMI during 2016-18, and is currently president of Mining Engineers Association of India, MEAI. He is also a member of the Executive Council of SGAT. With this, I now request Mr. Patnaik to please take over and start the moderation.
Thank you, Mr. Sujit Mohanty. Good evening, all the participants. And it's an absolute honor, pleasure, privilege, and delight to hear to Professor Bibhuti Mohanty. Sir, your presence has really been an eye-opener and has really been very educative for most of us. Besides that, there are many students, many young practicing mining engineers who have been invited to this talk. I'm sure your talk would have given them a lot of insight, and all of them are definitely enriched. So on behalf of SGAT and my own behalf, once again, welcome to you, sir, and profusely thank you for your brilliant talk. It was, in fact, wonderful listening to you on the various aspects of blasting, mining technology, safety, and economics, covering mostly the blasting part, the fuel, material science, safety, economics, geology. You covered it all, sir. And I'm sure there would be many. I was expecting many questions. So I find there are some questions in the chat box. And as our President, Professor Dr. Onkar Mohanty himself, a renowned person in the metallurgy field, metallurgy mining field in India, and having experience both in the industry as well as academia, has told that we would give priority to the industry representatives. If they have any questions, we would give them priority for you, and then followed by other questions and others. So I will straight go to the questions, sir, and we have, I will read out the name and then ask you the questions. This is there is a question from Yogita Shiva. Yogita Shiva. Her question is: are there any other rock breaking technology, non-destructive, to eliminate blasting, or which can eliminate hazards of blasting? Over to you, sir.
Yes, indeed, there are. As I mentioned briefly, continuous mining, where you use special bits to core out essentially. It's already being used for small scale tunneling. Eventually, you would like to combine the two, explosives and mechanical cutting. And there's been a lot of work by many companies, Sandvik, Sweden in particular, where we can drill our tunnels without the use of explosives. But then the same issue comes in, that is, we have known the rock response very well. As you know, rock strength can vary by order of magnitude. There are fracture toughness, there are strength, the whole material science comes into that. But there are emerging technology where you can do continuous mining, small scale, without the use of explosives. One of the problem with explosives is that, for example, underground tunnels, when you blast the explosives, you have to wait for 7 or 8 hours before the fumes clear. So essentially your work is stopped for a good part of the day because of the explosive. So there's tremendous incentive to go to non-explosive means, but there is no way you can do that kind of excavation in open pit where you can million tons of rock at the same time. But indeed there are, if you send me your reference or bearing, I can send you some literature on it.
Thank you. Thank you. I think that would have answered Yogita's question very well. There is another question from Puspendra Patel. The recent method of rock excavation in densely populated area surrounded by high-rise and old buildings.
Yes, there are. Every country, including India, has guidelines on the maximum particle velocity a building can withstand. That will depend on the age of the building, nature of construction of the building. So there are guidelines, very strict guidelines in India as well, Europe, North Canada, North USA, on what is the maximum level of particle velocity a building can withstand, and also the blast or wind velocity. In most cases, is not a serious issue. For example, coal mines in India are normally away from the urban areas. So, and there are not many high-rise buildings. So you could operate that with a great deal of safety. But there are issues, for example, in urban areas, when you're doing say for example, metro, you're blasting a metro tunnel in the middle of a city, and there are very strict guidelines, and I need special blast designs and special explosives. So I haven't gone to that. As I showed you, there are 100 different ways of initiating explosive. So indeed, there are several serious issues, but they are right now, I think, well managed in most countries.
Thank you. Thank you, Dr. Mohanty. The next question comes from Dr. Sudesh Kumar. He wants he requests you to throw some light on the impact of groundwater on rock strength and blasting operations. Impact of groundwater on rock strength and blasting operations.
The most problematic issue there would be the leaching, because as I said before, a typical mine, large mine, would put say half a ton of explosive in a borehole, and there will be 500 holes like this, but you don't blast them right away because it takes time to load the holes and look at all the other issues. Therefore, the explosives sit in the borehole for weeks, sometimes a month. All this time, the chemicals leaching into the groundwater, and that's indeed a very serious issue. And so sometimes we have borehole liners, but you can imagine the cost of lining each hole, which is 300 millimeter in diameter and maybe 20 meter in length with liners. And it's not practical, it's not economically feasible. So we have to work carefully with the environmental scientists, in that area and the blast designer to see that there's no excessive leaching of chemicals from the explosives into the groundwater. But it is a serious issue, especially for large operations like coal mines, etc.
We have a question from none other than our president, Dr. Mohanty wants to know, are there rocks where strain rate sensitivity is negative?
Not from any of the experiments I have done. The strain rate sensitivity is always a positive number. So some rocks are not as sensitive, but most rocks can, as I showed you in one example, one granite can be order of magnitude higher than the static strength or static effects of toughness. So I know of no rock material which would have a negative slope with rate of loading.
Okay.
Our General Secretary, Mr. Panigrai, he wants to know that can you throw some light on the economics of surface miner compared to blasting in large open cast mine?
Maybe I didn't understand the question. Even when is mechanical excavation versus blasting?
Yeah, large surface mines, yes.
Yes, it can be done in especially coal mines. The rocks are soft, mostly sandstones, and that can be done in coal mines, but it can't be done in hard rock mining like iron ore or precious metals. But for soft rocks, yes, mechanical cutting is quite viable and it's practiced. I see Professor Mansingh had a question.
Yeah, Professor Mansingh.
He has raised his hand. He can ask directly.
Yeah, you can ask directly to Professor Mansingh.
Yes, because
Okay,
he has
it's not a question, actually, two comments. One is in Bibhu's biodata, it was not mentioned that Bibhu and I were part of an Ontario delegation. The government of Ontario delegation to government of India were negotiating with the Indian Department of Mines to collaborate on mining research, related research with an institute that would be jointly run by the Indian School of Mines and by IIT Kharagpur. And but as in many such endeavors, nothing came of it. So maybe Bibhu can give you some more details. We had some wonderful research projects that we outlined that we would have done, Bibhu and I would have done jointly in Odisha. And the other thing is perhaps some members of SGAT may remember that I was part of a delegation of 4 professors from the University of Western Ontario that included Fred Longstaff, Robert Lennon, Gerhard Pratt, and myself. And we did visit SGAT, and Fred Longstaff gave a talk. And the part of the purpose of that was to invite collaboration on serious geological mining research issues that could be tackled jointly. And during that, we visited IIT Bombay, IIT Kharagpur, IIT Bhubaneswar, and of course SGAT, and they did visit Sukinda mines. But as again, nothing much came of it. So 2 initiatives that did not happen. That's all. And Bibhu, thank you for a talk. I threatened to make your life miserable, but I won't. So
I barge in. This is
That was
Omkar Mohanty, I barge in because these are very important topics, what Professor Mansingh mentioned. We can take them up perhaps after the talk because they are of great importance and relevance. But we'll come back to the topic first. Yes, Mr. Patnaik, Sanjoy, continue your questions. Continue through the questions list.
Yeah, right. There's a question from Mr. Rajgopal Mohanty. How far the heat has been found to dissipate due to blasting horizontal in rock mass?
When you say leaching, as far as I know, I don't know myself any information on that. Leaching is a serious issue, especially between the coal mining areas in India. But I don't know of any systematic study which has been done to study the percolation of the chemicals into the groundwater. I think best place for that would be India actually, because they have around maybe China also. We don't have many big coal mines in Canada or USA. We have, but not same scale as in India or China. So that's a very serious topic. People ignore. They think that you blast or you load the explosive and you forget about it, and then go afterwards and collect the rocks. I'll just go back to Professor Mansina's comment.
Yeah, it is me who had asked. In the context of sir, we were sometimes making study of radioactive waste disposal in the subsurface. So when the radioactive disposal, that radioactive heat also gets generated from the waste. So how far the heat gets transmitted inside the rock mass? Normally radioactive disposal is done in the granite terrain. It is never done in the sedimentary terrain. So in the rock, when the rock mass is homogeneous like granite, how far is any modeling has been done on the heat transmission inside the rock surface? That was my interest.
That was the question, sir. Heat dissipate. How far that was the question. But anyway, thanks for giving the another wonderful insight on the leaching part. But the question was how far the heat is found to dissipate due to blasting in rock mass.
On the heat, you mean the temperature rise in the explosion itself?
Sir, yes. How does the heat transmit?
It's transient. It's in milliseconds. Very transient. It doesn't hit up the rock like you would think that hitting the rock for weeks. No, it's the whole. For example, a typical borehole, the explosive will detonate at 4 kilometers per second. So the whole thing is finished in 2 milliseconds. So there is no residual heat being transferred to the surrounding rock mass. I'll just briefly go back to Professor Mansina's comment about this joint program we had started with 4 universities in Canada and IIT Kharagpur and IIT ISM to set up a center of excellence in mining technology. We had many visits. People from faculty came from ISM and IIT Kharagpur and the Ministry of Coal, the secretary, and secretary also, who also happened to be IIT Kanpur graduate. So we had extended sessions both in Toronto and in Delhi and in IIT Kharagpur and ISM. And we had quite a bit of funding from the government, Canadian government. After all that work, lasting over a year, we were told that the Center of Excellence in Mining Technology should concentrate on training Afghan miners. I mean, it's unbelievable that the secretary should come out and say that, okay, we'll support it, provided you train Afghan miners. I suppose they were told by the politicians that it's a very important thing, we should train the Afghan miners. So we have to return the money. I can't believe this. After all that work, we return the money to Ontario government. But it's sad. For this, I mean, I mentioned to Professor Mohanty the other day that even IIT is still pretty segmented. Disciplines don't talk to each other. So mining department at IIT Kharagpur, with which I'm associated, doesn't have much connection with material science or geophysics or geology. You can't do this thing or mechanical engineering for transportation, etc. So they all live in silos, unfortunately. And that's why IIT, no university in the world, in India, is ranked above 400 in the world. Yet we have IITians, ISMs everywhere in North America, in Europe, but no Indian universities is ranked in par with other countries. China has.
And we have Sundar Pichai's, Arvind Krishna, and Satya Nadella. And
I haven't. Yeah, that's right. Forgive my statement. I call ourselves techno coolies.
Right.
Yeah. In the old days, the British government sent coolies to South Africa, to West Indies, to Fiji, Mauritius. Only difference between us and them is that we have degrees from IIT or ISM.
Sanjay, can you take over again?
I think, yeah, I think, sir, maybe we hope that the times will change, and yes, that was your observation. And I think it's already 8, so we'll take the last couple of questions, sir. We have reached the scheduled time, but we'll take the last couple of questions. One is, this question is from, I'm not, anyway, Moto or something. Anyway, the question is, sir, is there any specific consideration required in designing fracture intensity and fracture orientation while blasting in order to effectively reduce the cost of crushing and grinding?
Yes, I didn't discuss this part in this small talk. We have I have a group who are working on numerical modeling of the blasting process, and there are also groups in IIT Kharagpur, especially Professor Devashish Dev, who are working on numerical modeling of blasting process and how to predict it. I didn't show you the graphs, pictures. Maybe another day we'll have this occasion, but it's quite a tough project to predict fragment size distribution and fracture network in a target rock, even for a homogeneous rock. So there's a lot of work being done at the moment, and hopefully another decade or so we'll be able to predict it with a high degree of confidence. Right now we can't. We still need empirical experiments. But as you know, material science is a very complex subject, especially for inhomogeneous material like rock. Because all these microcracks we generate due to blasting would help the grinding and crushing process immensely. But the idea is that we can't be doing experiments in a million ton of rock and say, oops, I made a mistake, let me do it again. So a lot of numerical modeling is being done at the moment, advanced numerical modeling. And hopefully in 10 years or so, we should have a pretty good handle on it. I didn't emphasize that part.
maybe he could give his email and we will contact him, and sorry, any further clarifications required by the questioner. He's not given his name fully, so maybe we'll get back to you through SGAT. The last question is from our Vice President, Mr. G.S. Khuntia. It's more of an information. He's wanting to know large open pit mining in Canada, USA. What is the frequency of cast blasting?
I didn't get the frequency of what?
Cast blasting. Maybe if is Mr. Khuntia there? Khuntia sir could ask the question directly. Our Vice President.
You have to open you have to unmute yourself. Mr. Khuntia, unmute yourself.
Okay, thank you. Sir, cast blasting means this is mostly used in dragline operation where very large scale material handling is done. So there, some of the rock masses, particularly overburden, is shifted horizontally. So that is used in very large scale operation, say 40 million ton per annum, 30 million ton per annum. I have seen also in Perth, Australia, Mount Newman mine, etc. They do blast as much as 4-5 million ton in one plant, Perth, Australia. But then how is the frequency? Coal India has tried some cast blasting, but how is the casting, how is the scale of operation of cast blasting in Canada and US, etc.? That's all I want to know.
Yeah, as many of you might know, we are not a big coal mining country. So we have very limited cast blasting opportunities. Same thing holds for USA, but certainly for China and India, Australia and India, it will be a very important issue to follow through. Again, this applies mostly to soft rock, not hard rock. You can do that, but in hard rock, cast blasting would not be possible. Also for precious metals, we don't want to mix up the grades. So as you probably know, a typical mine has the grades of the mineral varies from place to place. And for example, gold mining, you want to actually to not move the rocks, because your loader, the trucks come and dump it to a particular place in the processing unit. So we know what the grade of the ore is. You don't mix low grade with high grade. And that's very important. So in many mines in Canada and USA, we want the rocks to be only fragmented and just swell up and not move around, because we want the boundary of the ore bodies kept intact.
Otherwise, everybody will be taking away the gold. Or
no, sir. Excuse me. Cast blasting is done usually in overburden, not in mineral. Mostly done in overburden.
Anyway,
right. So that was the last question.
Mr. Patnaik, with your permission, I just wanted to say, Omkar Mohanty, I wanted to say that there is a question which I had put on the fracture toughness of a material like rock, which is a heterogeneous material. How do you define actually the fracture toughness for a heterogeneous material? For metallic materials, you have a specific value, and there in Society of Metals procedures for measuring the fracture toughness. What measure here for a heterogeneous material, a fracture toughness, and what would be the connotation of that? What would be the critical size, therefore?
Yes, the work we do, I've been doing for the last 10 years, is on homogeneous rock, limestone, and granites.
Right.
But we haven't tackled the issue of banded rocks.
Okay.
And that's going to be a tough one. But our work so far has concentrated on homogeneous rock like granites, limestones, but not on things that are like schist. We haven't done any work on schist or gneiss.
Right.
But also, if and when we do the work, we need to do a lot of testing to get an average value. Okay, so it's not that simple process. Although another point I didn't mention about the we have a lot of work going on right now in my group as well in measuring fragment size distribution by aerial technique. So if a camera or a drone which measures the fragment size distribution as the mocking is progressing, because that's a very big issue. You want to change your blast design. How do you do that? Because when you go to the crusher, in the crusher, rocks from all kinds of areas are mixed up, from the toe of the blasted rock to the three face of the blasted rock, and they have different fragment size distribution. That's one of the big weaknesses right now in the assessing a blast. What is a proper blast? Depends on where you take your samples. So with the drone, we can now do this as a function of time. So we have pretty good idea of the fracture size distribution. While I'm at it, since you're ending the program, I really express my gratitude for inviting me, and I'm very honored to. I'm told that I have become an automatic member now of SGAT. So please,
yes,
please feel free to ask me.
Membership formed by some of our people, by our treasurer and secretary, Professor Mansingh, yourself, Professor Didi Mishra, all of you. Yes.
Yes.
Professor Mansingh is already a member. Pardon me. Yes.
Yes.
Yeah.
He is a member already.
Yes. He's already a member.
May I add something to Bibhu's last comments? Some of the projects, experiments that the research projects that he mentioned would have been tackled in a very effective way by the institute that we were proposing, where the joint institute between Canada and India. So, and a lot of these require field testing. While he's doing numerical modeling, a lot of these require field testing, and this is what would have basically led the world in terms of validation. So,
I think
yes,
it's necessary. We can still take it up in Odisha somewhere.
Actually, I'm helping Professor Manoj Mishra at NIT, Rourkela, in proposing a large proposal for OMC to get a handle on it. So hopefully, the COVID has thrown everything off the target, but hopefully we'll have a multi-year project with OMC participation.
Back to Sujit.
Can we stop here? Yeah. Yeah, I thank Mr. Sanjay Patnaik profusely for moderating this session very nicely. Now I shall request Mr. A.B. Panigrahi, former Controller of Mines, Indian Bureau of Mines, and General Secretary SGAT, to please offer his concluding remarks and formal vote of thanks. Mr. Panigrahi, please.
Thank you, Mr. Sujit Mohanty. We have come to the end of the talk from Dr. Bibhuti Mohanty, and the moderation also has been done. And in fact, from the chat box itself, many of you must have seen the appreciation given to Professor Mohanty on the topic which he has chosen, particularly more focusing on the blasting aspects, fracture dynamics, and particularly at the end of the question and answer, he said, itself speak of an excellent presentation, which has been appreciated by one and all who have attended this lecture program, for
your audio is not working.
Presentation.
He has some internet problem.
I think Mr. Panigrahi, your microphone system is misbehaving.
It's internet problem.
I'll bring it to my.
Yes.
I request all of you to kindly join and give a very big hand to Professor Bibhuti Mohanty, who was given
While clapping, please unmute
excellent
yourself.
presentation.
You don't unmute yourself.
Thank you all very much for taking time out on a Saturday evening.
Our deep sense of gratitude to our president, energetic president, I will say, Professor Mohanty, who has been a great inspirator and a motivator. And every time he is following us about the distinguished lecture series. And in fact, his idea was to change the earlier our this name of this lecture series or invitation lecture series. Now we have changed it to this distinguished lecture series. So thank you very much, sir, for your kind words as well as welcome address also. Excellent welcome address.
So I think we have to say that the COVID has helped us blessing these guys in coming together from so many continents and
COVID has
countries.
given you wonderful for meeting the persons all across the world. So that is a change which we have seen in the COVID times. So my thanks also are due to both the vice presidents, Sri G.S. Kuntia and Sri G.P. Girija Prasad Mahapatra, and particularly Sri Girija Prasad Mahapatra was the head of the subgroup looking after the entire management of this entire DLS 3. That is.
I think we should thank people from a large part of India across the country, from educational institutes. I see people from BHU, from ISM Dhanbad, from, I don't know, I don't see a number of people.
President, may I come in?
Yes, please.
This is I'm Farooq speaking. May I come in for SGAT bulletin?
Yes.
Yeah.
I think we can
Yes,
before we end
discussing. Yes.
Okay. Right, Dr.
Yeah.
Farooq. So we are also extremely thankful to Sri Sanjay Patnaik, who has been was done a wonderful job of moderating the question and answer session after the lecture of Professor Bibhuti.
Dr. Farooq.
My sincere thanks are also Dr. Farooq, Dr. B.M. Farooq, Professor Madhukar Das, the entire WhatsApp group of distinguished lecture series.
Dr. Farooq wanted to
SGAT involvement group.
Mr. Panigrahi, Dr. Farooq,
bandwidth,
the problem is
the
in order
program
to make
is on shoot as well as yes.
Mr. Panigrahi, let's allow Dr. Farooq to speak, and after him you can complete your next part of the speech if you wanted to. But in order to overcome the problems of your bandwidth, you may switch off your video part. Your voice will come much clearer. Yeah.
Right, sir. I'll switch off the video part. Okay.
Yes.
Let Professor let Dr. Farooq speak.
Yes, please.
Yeah. Good evening, everybody. Actually, this is to mention the last component of our, this lecture series. We try to publish or record the presentation of this evening and bring it out in the form of a publication, which is SGAT Bulletin. And in the future issue of the SGAT Bulletin, we'd like to have this paper of Professor Bibhuti Mohanty to be, published. May I request, Professor, you take your time. There is no, you have the, freedom to take your time and then give us a brief paper. Not a brief paper, I mean the paper which you have presented today in the form of a paper.
Research paper, yes.
Yes, I'll be very glad to do that. I'll make it a little more systematic and focused, but take a little time.
It will be a privilege.
That, all the other professors who are present here, Dr. Farooq is our chief editor of the SGAT Bulletin, and he's a very eminent geologist himself. And so what he is requesting here is to all of you to contribute research papers to the SGAT bulletin part. And of course, Professor Bibhuti Mohanty would be most grateful to you for receiving a paper from you and even from other people also. And that's what Dr. Farooq is requesting. And so there are a number of people here who are doing a lot of research with their students. So Professor Bibhuti Mohanty can himself present paper. Some of your students short papers also. We would appreciate that. So in order to enrich the SGAT bulletin, that's the only way. Back to Mr. Ravi Panigrahi, our General Secretary.
I have switched off my video because
you are very much audible now.
So now I am audible, sir?
Yes, very much.
So I'll continue from where I have left. So we are also, without IT's intervention, it is not possible. And for YouTube streaming and all other IT requirements, Dr. Rajwal Mohanty, our Subhranshu Misraji, and Sri Devasis Parida, they have helped us quite a lot. We are really thankful to all three of them. We are also thankful to our sponsor. For the first time, we had a sponsor for the distinguished lecture series. So we are extremely thankful to the sponsor, SR Rumta Group, particularly Sri H. Majumdar, the managing director of Rumta Sons Private Limited, who has extended the support for this program, which has been conducted just now. We are also thankful to our overseas, particularly we have professors, overseas professors and overseas participants. And apart from that, also we had a number of members who have attended this program, along with invitees also. We have a number of invitees. Where without your participation in this program.
Mr. Panigrahi, a small intervention here on that particular point. I once again come in, Omkar Mohanty. I want to make also a request to all the professors from outside, from overseas, as well as professors in other places in India, that would it be possible to have branches of SGAT in some of your places so that your other faculty, younger students, research scholars can also take the membership of the SGAT, some of them at least, and we can take SGAT across the country. Already there are a very large number of members, but SGAT is functioning only from Bhubaneswar, and we intend to moot the idea that we should actually start operating in various groups, in another 2-3 groups, not many. And would that be possible? We will try to collect some of your views on this matter later. But this is an idea I want to reside in your minds. Thank you, Mr. Panigrahi. Back to you.
Okay. Last but not least, we are also thankful to our all the colleagues who have contributed directly or indirectly, supported in every way for this conducting this program. Thank you very much. And with the permission of the President, we can formally close the program. Close this.
So namaskar.
The session is over now.
Stay safe. Stay safe.
Thank you. And
Thank you.
Stay safe.
Good night.
Thank you. Good night. Namaskar.
Namaskar.
Namaskar.